Hello, my name is Jacob Hummel, and with me is
And I'm Clay Holbert.
this is the Whirlpool gasket fixture project. We This project has been going on for 3 years now, and is for Whirlpool refrigerator door gasket.
So the current design focus is primarily on the integration of sensors and actuators upon the previously existing mechanical structure. And this is in order to simulate the functionality of the device via a Labview graphical user interface. This graphical user interface enables precise control of actuators and displays measurements of laser distance sensors. Additionally, this will make it easy for the device's operator to identify the optimal gasket placement within the testing parameters.
Uh, just a quick overview of the GUI itself. In the center, we have what's supposed to mimic the door and the placements of the lasers. As you can see, there's three at the top, three at the bottom, two in the middle. On the side, with the hinge side investigation, you can put an entry in for what test you're going for, shear, non-roll, or roll or non-reach. And that just is supposed to uh, organize the testing and determine what property of the gasket you actually want to test. On the left, there's model information, so you can put in a model number so it can be tracked later on for graphing and for saving the data. Below that is the sweep, uh, where it this is how the lasers actually read the distance. You put a number of the distance, higher input, and then a lower set input, and it sweeps between those 2 points to then narrow down to the actual distance read from the sensor itself. On the left is the pre-experiment checklist. This can be defined and will be defined later on by the Whirlpool operator for criteria following the SOP that will be created um, to follow the checklist and make sure they're on track and doing the right steps for running the tests.
On the right side of our GUI, uh, you're able to see the motor controls. It is paramount to ensure the synchronization of the stepper motors and linear screw drives that serve as actuators. Here we see that we are enabling slaves, so we're able to slave the x-axis and y-axis independently so that we may synchronize and tie both motors together.
Uh, there's two movements, feed to position and increment. Feed to to position is to set the beginning distance from zero or home. That is actually hardware onto the actuator themselves with a proximity sensor. If I feed to position on the x-axis, 10 millimeters, and click the button, the graph or the GUI itself updates and tracks the distance. Same with if I increment it to -1 millimeters, it will update the graph and move in and have the GUI update. Um, this works for both X and Y axis. Same with Y. We can feed a distance from feed to position and increment in or uh, increment out. Um, Another important button that we have within our GUI is the Save Investigation button. Uh, this allows for the data that we have to be saved into a separate folder um, that can be either created or uploaded beforehand into our template, and it saves it as a CSV file. Um, for example, as a quick rundown for an actual demonstration of the sweep, we can input a high input of distance and a low input of distance. and the lasers will slowly sweep for distance. This takes quite some time, as parallel processing in Labview is a difficult thing to achieve. But in the meantime, I will be talking about the back panel of how the GUI kind of operates and flows. We have an event case structure feeding into a case structure surrounded by two while loops, with uh, a VI block, a sub VI called next action. Um, on the left is any button or any interaction of the GUI, and the constant box of the string will be able to input a series of commands that it will then do upon activation of the button. Um, and it will perform those actions one by one, um, to ensure proper functionality of the fixture themselves. We cannot show too many of the sub VIs, as that is breaching agreement with us and Whirlpool to not show any hidden trade secrets or hidden data that they will need to protect. As you can see, our sweep has completed and updated um, to a series of distances. And upon saving investigation, again, we can save that data into our just freshly created or templated CSV file. This data is then imported into Google Sheets to show it on a graph with numerous samples, so Whirlpool operators can gather meaningful data across different model gaskets and different model inserts. Uh, Thank you for showing up to this demonstration. Uh,
We appreciate your time. Thank you so much.
Thank you.
Hello, Senior Design Expo team. This is the Whirlpool Gasket Data Acquisition System Part 2, showing off the hardware of the system. So here we see the control panel. This being a heavily automation-based project, we focused a lot on the networking and the data communication of the devices between the laptop and the individual stepper motors and laser distance sensors through using a WAGO Ethernet switch, allowing for one Ethernet cable to provide to facilitate communication back and forth between devices. Here we see the actual fixture itself. Laser mounts were designed and 3D printed out of carbon composite. This is the outer door as it stands currently. Here we see the linear actuators that move the door hinges along the X and Y axis. And here we can see the proximity switches we used as homing positions for the linear actuators. So now we're going to demonstrate for you the actual movement of the device. Yep. Here we can see how the Y-axis is synchronized together. Now movement of the X-axis.